In this video I want to talk about Boolean algebra as a more fundamental level. I will go through some axioms and theorems and ways that we can simplify Boolean equations. Boolean algebra is based on several axioms and theorems that help us to simplify Boolean equations. Like regular algebra, we can use these axioms and theorems for simplification, but it is much simpler because unlike regular algebra, here we only work with variables that have two values, either 1 or 0. So because of that, some of the rules can be simplified, and also there are some cases for which we have conclusions that are completely different than regular algebra. I will point out to them at a later slide. So there is a concept of duality in axioms and also theorems, in which ands and ors and zeros and ones are interchanged. So if you have an axiom, you can simplify, create its dual by changing any and that you have to or any zero that you have to 1. The same is true for theorems too. So now that we have these things, let's just go through the basic theorems and axioms that we have. So the first axiom that we have, here we call it A1, states that B is 0 if B is not 1. So B is the logic variable that we have that can either be 0 or 1. So the first one, which is called the binary field axiom, is very intuitive. B is 0 if B is not 1. Its dual says B is 1 if B is not 0. So this is something that you can easily comprehend. The next one is the not axiom, which says 0 bar equals 1. So basically, if you have a variable to be 0 and you complement it, you make it 1. The same is true for 1 as well. 1 bar equals 0. So what is not 1? The answer is 0. Or what is not 0? The answer is 1. Then we have these three axioms. We call them and or axioms, which says that 0 and 0, so this is representing and, this dot. 0 and 0 equals 0. In another word, 0 multiplied by 0 is 0. In its dual form, 1 plus 1 equals 1, or 1 or 1 equal 1. So this represents or. And if you remember from before, I said that there is a subtle difference between plus and or, right? So this is not 1 plus 1. This is 1 or 1. If it was 1 plus 1, the answer would be 2, or in logic form, in binary form, 1 plus 1 equals 1, 0, right? So this is or. And as you can see, based on what I said, to go from the axiom itself to its dual, we interchange all the zeros with ones, and we interchange the and with or. Axiom 4 says 1 and 1 equals 1, or 1 multiplied by 1 equals 1. In its dual form, 0 or 0 is 0. To be able to understand this easily, you can consider 0 to be equal to false and 1 to be equal to true. So in that case, these make more sense. So false and false equals false. True or true equals true. True and true equals true. False or false equals false. And finally, A5 says 0 and 1, which is equals to 1 and 0 equals 0. So true and false combined equals false. Its dual says true or false, which equals to false or true equals true. So these were the 5 basic axioms that the Boolean algebra is using them as the foundations for itself. So now, based on these axioms, we can derive some simple theorems. So in these theorems, which I listed them here from T1 to T5, we have introduced a variable named b, which is either ANDed or ORed with 0, 1, or itself. So the first one that we have is the identity theorem, which says b and 1 equals b. So let's just see what each one of these theorems says in a more visual way. So for the identity theorem, we have b as a variable, which is ANDed with 1. And we say that the answer is b itself. So this is, visually speaking, this is equal to ANDing b and 1 using this AND gate. And the answer to that is going to be b itself. So this, you can say, this is the Boolean equation expression. This is the schematic expression. We can create a truth table expression too. So we have variable b, we have another variable which is always 1, and we want to find the output y here. So b can be either 0 or 1. The variable 1 is always 1, right? So now what is the value for y? 0 and y is basically b ANDed with 1. 0 and 1 equals 0. You see here, based on A5. 1 and 1 equals 0, again, based on A4. So these are the axioms that we already talked about and we already agreed upon. So using those axioms, we can easily verify that y is exactly equal to b. And that is what the identity theorem represents. So if you AND b with 1, the answer is going to be b. So in some sense, this one, this you can say it's equivalent to b going through a simple buffer. The other input, since it's 1, doesn't change the value for the output. In its dual form, we interchanged any AND with OR, and we interchange any 1 with 0. And we get to b or 0 equals b. So basically, if you OR any variable with 0, you get the variable itself. And you can easily create the truth table as well. So we have b here, we have 0 here, so b can be 0 and 1, 0 is always 0. If we have y to be equal to b plus 0, based on A4 again, when we have, or A4 prime, the dual of A4, 0 or 0 equals 0. So this is equal 0. And then we have 1 or 0 which equals 1. So 1 or 0, that is A5 prime equals 1. And then you can again see that these two columns are exactly equal. So that is why what we have as B or 0 equals B. Again, this is equivalent to B going through a simple buffer. So this way of proving the two sides of this equation is called a perfect induction. And it is a very common way to prove the equality of Boolean equations. Since we are working with Boolean equations and binary values, there is a limited number of possibilities that those values can have, right? So what we basically do here, we verify this equality, whatever equality that we have between two Boolean equations, by considering all the possible combinations. So if that equality is true for all the possible combination, then we say that this equality is true, right? So that is something that you cannot easily say about the regular algebra. But for Boolean algebra, since the variables have limited number of possible values, you can easily prove any equality that you see, and verify whether they are true or not. So the next theorem that we have is called the null element theorem, and we can again use the basic axioms to prove that they are correct. So the null element theorem itself specifies that if you AND a variable b with 0, the output is going to be 0. You can think of it as a multiplication. If you AND or if you multiply any variable with 0, the answer is 0. And that's basically what we have here. We can use the perfect induction the same as before to verify this as well. This one is 1, 0, and then here y is b ANDed with 0. So 0 and 0, again based on one of the axioms, it's going to be 0. 0 and 1, it's going to be 0. And as you can see, this column is exactly similar to this column. So that's why we say b and 0 is 0. What about its dual? Again, we interchange any AND with OR and any 0 with 1. So for the dual case, if we OR any variable, no matter what's the value, whether it's 0 or 1, if we OR this variable with 1, the answer that we get is 1. So the variable itself does not matter, and that is what is called the null element theorem. So 0 is the null element for the AND gate. Basically, if you AND any variable with 0, the output is 0 always. So basically it nulls the effect of the other variable. For the OR gate, 1 is the null element. So if you OR any variable with 1, the output is always 1. So it looks as if the other variable does not have any effect, right? So that is why it's called the null element theorem. Then we have the idempotency theorem, which states that if you AND a variable with itself, the output is going to be b. And that is one of the things that it is different from the regular algebra. So with regular algebra, So let me just say this is not equal to regular algebra. So in regular algebra, if you had b multiplied by b, the answer was b squared, right? But in Boolean algebra, ANDing b with itself results in b. In its dual form, when we switch all the ANDs with OR and all the zeros with 1 and vice versa, we get to b plus b equals b, or b or b equals b. And again, this is different than having b plus b in regular algebra, which is 2b. Why is that the case? The reason is that b can only be 0 or 1, right? So since it can only be 0 or 1, that applies to any result as well. So b squared in regular algebra, if it only could be either 0 or 1, then we get to the Boolean algebra. Or 2b, if b is 0, 2b is going to be 0. If b is 1, 2b in Boolean algebra can only be 1, right? Because we can only have either 0 or 1. So in a schematics form, that is equivalent to ANDing b with itself, which results in the value to be b. Again, this is equivalent to b only going through a simple buffer. The same is true for the dual 2. ORing b with itself results in b. Again, this is equivalent to b going through a buffer. Basically, the value does not change. So this is what is called the idempotency theorem. Then we have the involution theorem, which is very intuitive, which says that if you complement the complement of b, you get the b itself, right? So if you have b and b goes through one NOT gate, you have b bar. If b bar goes through another NOT gate, you should get b itself, right? So if b is 0, after one NOT gate, you have 1. After the second NOT gate, you have 0. If b was 1 to begin with, after one NOT gate, you get 0. And after another one, you get 1. So as you can see, b and b bar bar are exactly equal. So this is the involution theorem. And finally, for T5, as one of the basic theorems, we have the complement theorem, which says that b ANDed with b bar is going to be 0. Or visually speaking, if you AND b and b bar, the answer is always 0, no matter what the value of b is. We can easily verify this using the perfect induction too. So we have b here, we have b bar here, and we have y to be b multiplied by b bar. So when b is 0, b bar is 1. When b is 1, its complement is 0. So ANDing 0 and 1, the result is 0. ANDing 1 and 0, the result is 0. And you can refer to the axiom that basically built this foundation for us, right? As for the dual theorem, we have to switch all the ANDs with ORs and all the zeros with 1s. So this one states that if you OR b with its complement, the output is going to be always 0. And let me just quickly verify this using perfect induction. So y here is b or b bar. So if b is 0, b bar is 1. If b is 1, b bar is 0. So 0 or 1, the result is 1. 1 or 0, the result is 1. So as you can clearly see, this is how you can simplify your Boolean equations too. We will see more examples later on too. So here is the summary of the basic theorems that we saw so far. We have the identity theorem, we have the null element theorem, we have the idempotency theorem, the involution theorem, and the complements theorem. Based on these basic theorems and the axioms, we can have a set of more complex theorems that work on more than one variable. So the first one is the commutative theorem, which is very intuitive, which states that if you have B and you AND it with C, the result is going to be the same if the order of these two variables have changed. So B and C equals C and B. So the order does not change the result. And it is true for the AND operation. As for its dual, we replace any AND that we have with OR. And again, it says that B or C equals C or B. Very intuitive. The next one, which is the associative theorem, says that if you have three variables, you have B, C, and D, and you want to AND them together, it doesn't matter whether you find the AND result between B and C and then find the result of this AND with D, or if you find the result of AND of C and D and then AND the result of this calculation with B. So in another word, the order of these operations does not matter, right? You can even say this is equal to B and D ANDed with C. So this is exactly the same too. In its dual form, we just simply replace any AND that we have in our initial equations with OR, and it still works. The next theorem is the distributive theorem, which is again very intuitive. If we have B ANDed with C and we OR the result with B ANDed with D, that is similar as to factor out B, calculate the OR of C and D, and then AND the result here with B, right? So this is something that you have seen in regular algebra too. So in regular algebra, if you have B multiplied by C plus B multiplied by D, you can easily factor out B. First calculate the summation of C and D, and then multiply that with B. So let's say if B is 5, C is 2, and D is 3, right? So this equals 10 plus 15, so 10 plus 15, which is 25. The other way, 5 multiplied by 2 plus 3 is again 5 multiplied by 5, which is 25, right? So as you can see, these two are completely equal, right? So this is something that you have seen in regular algebra too. However, you cannot say the same thing about it's dual, right? So to create this dual, we replace any ands that we had with ors, and any or that we had with and. And we did it for both sides of the equal sign. So in Boolean algebra, if I rewrite this, we have B or C multiplied by B or D, which says it's equal to B plus C D. Can we say the same thing in regular algebra? B plus C multiplied by B plus D, is it equal to B plus C multiplied by D? The answer to that is no. So let's just use the same variables as before. So for the left side, we have 5 plus 2 multiplied by 5 plus 3. So 7 multiplied by 8, it's 56. The right hand side, it says 5 plus 2 multiplied by 3. This is 10. And you can clearly see that these are not equal. So that is another difference between Boolean algebra and regular algebra. That the dual of T8 or T8 prime is only true for Boolean algebra, and it is not true for regular algebra. So something that you can easily prove for these equations or these theorems is to use again the perfect induction to go from one side of the equal sign to the other side. So if I erase this, I can do it for one of them, so you have a better idea of how this thing can be done. So let's try to do it for T9, or the covering theorem. So here it says that B ANDed with B plus C equals B. This is something that you can see is also different from the regular algebra, as it's only true since our variables are zeros and ones. So let's just create a truth table for the perfect induction. We have B, we have C as the inputs, and let's just create B and B plus C, basically the two parts of the left hand side, and then we want to see what is the output, y equals B and B plus C. So since we have two inputs, there are four possible combinations. We have 0, 0, 0, 1, 1, 0, and then 1, 1. Again, I rather put these in order, so everything is more streamlined, and if I make any mistake, I can easily identify it. So here, this is B itself, so we don't have to do anything for that. For B plus C, or B or C, we need to use one of the previous axioms to find out what is the value. 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 and 1 is 1 or 1 is 1. So now to create the output for y, we have to calculate the AND of B and B plus C. So AND of 0 and 0 is 0, AND of 0 and 1 is 0, AND of 1 and 1 is 1, and AND of 1 and 1 again is 1. So now if you pay close attention, you see that this column is exactly similar to this column, which basically says that B and B plus C equals B itself. This is what is called the covering theorem for Boolean algebra. You can easily prove the dual as well. So we talked about T9 as well. What about T10? T10 is called the combining theorem. Let's just go through the proof of this one as well, just so you know how this thing can be done for each one of these. And if you can do this for let's say 1, if you understood how to do it for 1, basically any equality Boolean equation that I give you, you can easily prove it, prove to see whether it's true or not by perfect induction. So here we have B and C plus B and C bar equals B. So one thing that you might notice here is that for us to prove this, we don't necessarily need to do perfect induction. The answer is much simpler, right? So if we use T7 and we factor out B from these two terms that we have, so let's just use T7. So that means that the left hand side is going to be B ANDed with C plus C bar, right? So this is the simplification of the left hand side. So what do you see here? Which one of the basic theorems is this one? The complements theorem. So this is the complements theorem. So based on the complements theorem, the result of this term, C or C bar, is always 1. So now basically we proved that B equals B, which is something that we know is true, right? B equals B. But as you can see, for each one of these theorems, you can use any proven previous theorem or axiom to prove them, right? So it doesn't necessarily have to be the perfect induction. So this one, going and using the associative theorem and the complement theorem, you could easily prove it. Of course, you can use perfect induction too. For its dual, anywhere we had an AND or, we just replace it, we just switched it. So any AND is changed to OR, and any OR is changed to an AND. We have T11, which is called the consensus theorem. Is a bit more complicated than the previous one because now we have 3 variables. So let's just quickly go through the proof. For this one, I use the perfect induction. So we have 3 variables. So let me just rewrite it again here. BC plus B bar D plus CD equals BC plus B bar D. So as you can see, sometimes I put the dot, sometimes I don't put the dot, right? So these are equivalent. So whether I put the dot or not, when I write two variables or their complements next to each other, that basically means that they are ANDed together. So now let's see, what do we have for this one? We have B, C, D. Since we have three variables, they have 8 possible combinations. 0, 1, 0, 0, 1, 1, and then you continue this until you get to the last one, 1, 1, 1. We have B, C here, we have B bar D here, B bar D here, B bar D here, we have C, D here. So for each one of them we can easily calculate the value. So 0 and 0 is 0, 1 and 0 is 0, 0 and 0 is 0. For the next one, 0 and 0 is 0 again, 0 and 1, sorry, 1 and 1, you see this is B bar. So B is 0, which makes the B bar to be 1, and D is 1. So this is 1, and then finally CD is 0. So you can fill out this table all the way to the end. And then the final result, Y is basically the OR of all these terms. So B, D plus CD. So this will be for the left hand side. So this is, for example, 0, this one is 1, and you do this for the rest of them as well. So this is the truth table for the left hand side. You do exactly the same for the right hand side too. And if the two columns for the left hand side and the right hand side are exactly the same, this theorem is being proved. Of course, that is one of the ways that you can prove this theorem. There are other ways too. So you can use the previous theorems and axioms to do the proof as well. I'm not going to go over them. You can easily look it up and find out the truth. It can be done in a few lines of Boolean algebra, right? I'm not going to go through it here. I want you to be able to find these things on your own as well. And then finally we have T12, which is called the De Morgan's theorem. And probably out of all of these, this is one of the most famous one, or the most important one. And it is clearly obvious because all of the before ones, they had descriptive names, but this one has a, I would say, a more specific name. It's basically named after some mathematician. So in its basic form, you can have only two variables, but in its general form you can have more than two variables, and you will see at a later slide how the De Morgan theorem can be useful. So let's just go through some examples on how we can use these theorems to simplify Boolean equations. So for the first example, we have AB plus A bar B. So what we see here between these two terms is that B is common between the two. So one thing that you can do is that you can factor out B, and then inside the parentheses you can have OR of A and B. As you can see here, I use the commutative theorem as well. I changed the order first. So now we have A plus A bar. And we know from the complements theorem that this equals 1. So now this equation is simplified to only b. So this was a very basic example that we saw we can simplify using Boolean algebra. If you want more detail, this is the same simplification but with mentioning all the theorems that we have used. We used the T8, we used the dual of T5, and finally we used T1. Of course, you don't have to memorize the name of the theorem, only the concept. Let's just take a look at another example. So here we have A ANDed with AB plus ABC. So inside the parentheses, we see that we have AB in common between the two terms. So we can factor it out. So we have AB multiplied by 1 plus C. Based on one of the theorems, more specifically the null element theorem, we know that this is 1. So ORing any variable with 1 is 1. So that means that this is now simplified to A, B. Also, we had another theorem which said that any variable ANDed with itself results in the variable itself. So that means that A and A is A. So that basically says that the final result, the simplified representation for this equation is AB. If you wanted it much more detail, here is all the steps with the mention of all the theorems that we have used to get to the final conclusion. So even though these theorems are being used for the simplifications, you are not guaranteed to get to the most simplified result, right? Especially when you have more than two variables, right? It is very hard to use only the theorems to get to the most simplified result. So you should know how to work with theorems and axioms, but we will see later on a more visual and more appealing method to do the simplifications. So now let's talk about the De Morgan's theorem. So if you remember before, one of the things that I mentioned was that when we are calculating the complement of an AND, this is not equal to calculating the AND of the complements themselves, right? So you remember this one from before. And it is easily verifiable using perfect induction too, that these two are not equal, right? De Morgan theorems gives us a way to convert any AND to OR or any OR to AND. So when we have this term AB bar, right, basically the complement of the result of AB, that is equal to A bar plus B bar. Let's just quickly draw the truth table and come up with the conclusion ourselves. So this one, let's just say it A bar, B bar, sorry, AB bar, and then we have A bar plus B bar. So when we have two input variables, we have four possible combinations. Again, I put them in order. So what is the result of AB bar? This is practically the result of NANDing A and B. So A and B is 0, so that means that the NAND is going to be 1. 0 and 1 is going to be 0, so that means the NAND is going to be 1. 1 and 0 is 0, NAND is 1, and then finally 1 and 1 is 1, so that means the complement or the NAND is going to be 0. So now let's just do it for the right hand side of the De Morgan's theorem. A bar or B bar, so A is 0, B is 0, 0 bar plus 0 bar. 0 bar is 1, so we have 1 here. For the next one, we have again A bar or B bar. So 0 bar plus 1 bar. 0 bar is 1, 1 bar is 0. So this is again 1. The same analogy can be applied to the third row. And finally for the last one, we have 1 bar plus 1 bar. So 0 plus 0, which is 0. And if you look closely for this column, it is exactly the same, which means that the two sides of the De Morgan's theorem, AB bar and A bar or B bar, they are exactly the same. Visually speaking, this is equivalent to having A, B NANDed together, which is equal to ORing A bar and B bar. So this one you can write it like this as well. So this one is Y, so you can write it like this. This circle basically signifies the NOT operation. So in logic gate, whenever you see circle, that means that it is a NOT operation. For transistors, it is a bit different, so I don't go into them. You have seen it in NMOS and PMOS transistors. For logic gates, whenever you see a NOT, that means that you are performing, whenever you see a circle, that means you are performing a NOT operation. For the dual, what we did was that anywhere we had an AND, we replaced it with OR, and anywhere we had an OR, we replaced it with AND. You can easily verify the two sides of the dual of the De Morgan's theorem using perfect induction as well. And I highly suggest you do that. There are other ways that you can prove this as well. If you look for the proof of De Morgan's theorems online, you see mathematical proofs as well that use the previous theorems that we discussed to prove this. The proof is a bit more involved. I leave it up to you to go and look it up and see how it can be done. Visually speaking, the dual of the De Morgan's theorem says that if you NOR A and B, that is equivalent to ANDing the complement of A and B. So again, this one is equal to ANDing A bar and B bar. Again, this NOT is signifying, these circles are signifying the NOT operation. So why and how can we use the De Morgan's theorem? Through a technique that is called bubble pushing. So bubble pushing happens when you have a circle or a NOT operation and you want to change the location of this NOT. If it's at the output, you want to make it go to the inputs, or if it's at the input, you want to make it to the output. So because of that, we have two forms of bubble pushing. We have a backward bubble pushing and we have a forward bubble pushing. So for the backward bubble pushing, we have the circle at the output of some gate, either AND gate or OR gate. One thing that you should keep in mind is that all the concept that we have described in this lecture only works for AND and OR. So don't confuse them with XOR or XNOR gate, right? So they are not involved here. Here we have either AND or NAND or NOR and buffer or NOT gate or complement gate. So as I was saying, Backward bubble pushing is when we have the circle at the output of an AND gate. In this case, when we push the bubble from the output to its input, the body of the gate changes. So if it's an AND gate, it changes to an OR gate. And then we have bubbles at the inputs. So as you can see, we had one bubble at the output of this AND gate. We pushed it through. The gate has changed from an AND gate to an OR gate, and now we have two bubbles at the inputs. So this is what is called the backward bubble pushing. For the forward bubble pushing, we have bubbles at the input of an OR gate. When we push the bubble from the input to the output, what happens is that the body of the gate changes. So if it's an OR, it becomes an AND. And then we have to have bubbles at the output of the gate too. So here you can see this is the complete opposite of what we saw before. So here we had an AND gate, we changed it to an OR gate with bubbles for the inputs, and here we have an OR gate with bubbles for the inputs, and we changed it to an AND gate. So let's just take a look at one example and see how this thing can be done. So first of all, let's just write down the expression for this Boolean equation, for this schematics. So we have A here, we have B here, they go through an AND gate. So the output is A, B, bar. The same is true for this one too, NAND gate. So this is CD bar. Now they both go through a NAND gate, another NAND gate, which makes the output to be AB bar, CD bar, and then one bar on top of that. So as you can see, this one is the output for this schematic. But one thing that you might notice is that this is somehow very convoluted. Is there any way that we can simplify this? So the way to do it is using bubble pushing. So to do bubble pushing here, we start from the output from this bubble, and then we push it forward. So if I do that, as I said before, the gate changes. Since it's an AND, it becomes an OR. And now we have bubbles at the inputs of the gate. So let me just draw this one, this is the other one, and then we have A, B, and C, and D. So what do you notice here after the first step of bubble pushing? Here we have a knot, here we have another knot. So don't they cancel each other? Do you remember when we had, let's say, x complement was the x itself, right? So that means that these two bubbles now cancel each other because they are applied to the same wire or the same node. So based on this, what I can do is I can simplify this even more. So let me just quickly draw the simplification. So we have A, B going through an AND gate, C, D going through another AND gate. So this is A, B, C, D. And then since the bubbles are cancelled, now we have simply one OR gate that creates the output Y. Now if I write down the equation for this, Y is equal to, here is AB, here is CD, so it is AB plus CD. So this one is Y2. So these two are completely equal. But this one is less convoluted. There is no complement. It is simply an AND, basically two ANDs followed by an OR. But this one was a bit convoluted. You had one AND and then complement. You had another AND and then complement. You had a third AND and then the complement, right? So this is a much easier way to represent this function. And we were able to do it all thanks to pushing the bubbles from the outside to inside. For bubble pushing, there are some rules. The first rule is that we begin at the output and then we work ourselves toward the input. We push the bubbles on final output back, and then we draw the gate in a form so bubbles cancel each other, right? That's basically what we did intuitively for the previous example. So now we put them as a few rules that we need to follow. We begin at the output of the schematic, and then we work toward the input. We push bubbles on final output back first. So that is kind of the first rule, saying it differently, and then finally we draw the gates in a form so we can cancel the bubbles. So let's just take a look at another example. We have A, B going through an OR gate. The result is going through an AND gate. And then finally we have another NAND gate that creates the final output Y. So if I want to write down the function here, so here, sorry, this one is NOR gate. I just wanted to make sure that I didn't make the same mistake in the previous slide. So this one is NOR gate, NAND gate, and then NAND gate. So if I want to write down the equation, here we have an OR gate, so this is A or B bar. Here we have C and A or B bar, and then a bar over top of it, and then finally Y here is D ANDed with C ANDed with A or B bar. This one has a bar, and finally this one has a bar, right? So as you can see, it is very convoluted. What we can do is that we can push the bubbles. So let's just start from the last step and push the bubble forward. So if we do that, what we have is the gate is changing from a NAND gate to an OR gate. We end up with bubbles at the input. So this will be the first step. So this one, we still have it. This NOR gate, we still have it. And then here we have C, and then here we have D. So this is A, this is B, and this is the NOR gate. This is the NAND gate. So one thing that you can see here is that this bubble and this bubble, they can be cancelled because they are applying to the exactly same node. And this one, we can just easily transfer this to the input itself, right? Now what is left is we can push the bubble here too. So let me just rewrite it with the bubble pushed through the this NOR gate as well. So the NOR gate becomes an AND gate. Now we have bubbles at its input. So here is A, here is B. This goes through an AND gate, for which the other input is C, and then this one goes through an OR gate, for which the other input is D, right? And it has a bubble too. So this one is Y. So this is the first, basically the last step that we need to do for pushing the bubbles. So now if we want to write down the equation for this function, we have A bar, B bar. The result of this AND gate is going to be A bar, B bar, C, and finally the output is going to be A bar, B bar, C plus D bar. So these two equations are completely equal, but this one is much simpler to comprehend and is less convoluted. You can see it much cleaner here too. So we started from a very convoluted equation and we ended up with a much simpler equation by pushing the bubbles, or in another word, by using the De Morgan's theorem, right? Bubble pushing is equivalent to the De Morgan's theorem. So in this video, we learned about the Boolean algebra, the axioms and theorems that are being used as the foundations for Boolean algebra, and we can use them to simplify the Boolean equations that we have. I introduced the topic of duality, how we can use the duality or the rules for duality to go from any theorem to its dual. We had to interchange any ORs with ANDs, any ANDs with ORs, any zeros with ones, and any ones with zeros to get to a dual of an equation. I introduced the De Morgan theorem. We proved it using perfect induction, and then we saw how we can use the De Morgan's theorem as means for pushing bubbles to simplify the Boolean equations and logic circuits.